Welcome to Regents Physics Warm Up. Feel that heat? This is a 7-part review in preparation for the physical setting physics Regents Examination. I, your host, Mr. B, will lead you through not memorization but process skills. There are many processes involved in completing the Regents Examination successfully. So, let this warm you up, both before you're studying and right before the test. Our video episode today will be Part 5. Part 5, taking down the big game. As with all parts of this review, follow these steps both during practice and during the examination. It is not practice that makes perfect, but it is perfect practice that leads to perfect execution. All right, let's go. So, big game, number 1. What if I get a multi-component circuit, meaning more than one lamp and or resistor? Don't try to be smarter than the question. We've created something called a whole part VIRP chart, and that will keep you honest. Yes, the question may end up being easy. Oh, you feel like this was too much, but you know what? It will organize your givens, and you will get the right answer. So the process, set up a chart like you see over here. We're going to do this on the next page. You're going to fill in what you know, and then use the rules of the reference table to get the rest. Let's go. Okay, here's a question. Notice that there are 3 lamps and 1 battery, 1 source. Regardless of what the question is asking, particularly since there are multiple parts, it's a safe bet. Set up that whole part VIRP chart. So notice here we have the whole, and then we have 3 parts, the 40, the 60, the 100. It's good to identify which is which, so we can call this part 40, part 60, part 100. Divide them. Run the row across. Up here in the top left, be sure to identify the type of circuit you're working with. This is a parallel circuit. Remind yourself that when you are working on the rules, you will be focusing on the parallel circuit rules. Of course, this same process works for series circuits. You just simply use the series rules. So VIRP, whole part, we got that set up. VIRP, V-I-R-P, VIRP chart. You can actually continue this chart if need be. You can add a W for energy. You can add a Q for charge. But typically, we're answered with VIR, and sometimes we need P. In this case, clearly we do. There are powers given. So the first rule is just add everything you know. Whole also refers to the battery. So notice here the potential difference of the whole circuit is 120 volts. Okay? We also know the power in the individual parts. So the power for the 40 watt, of course, is 40 watts. Power here is 60 watts. Power here is 100 watts. Okay. Now, you can start filling things in. One of the questions that's asked, 8182, is actually find the resistance of the 40 watt lamp. So you come over here. Resistance is actually your question mark for the 40 watt lamp. Now, you have 2 choices on how you approach this chart. One of them is to use the equations that are written in the standard electricity part. Typically, those equations are Ohm's law and the power and energy equations. Occasionally, you can use the current or V equals W over Q, but these 3 are really the big 3. You will use those within any particular column. So within the whole column or one of the part columns, one at a time, you can use those rules. If you want to go across a row, meaning connecting the whole to the parts, that's when you jump down to the parallel circuit rules. So here, in this case, one of the convenient parallel circuit rules is the potential difference rule, where it's the same in each of the branches as it is for the battery. So if we use that rule up here, we know straight away that the V is 120, 120, 120, straight across the chart. Please don't assume you know what the rule is. Just go look it up to confirm. You don't want to mix up the voltage rule and the current rule because you didn't pay attention to which set of rules. All right. This actually is enough for us to answer our question. In fact, now we can go down the column, the P40 column, and we can use the equation for power that relates potential difference and resistance. That would be power equals V squared over R. So P equals V squared over R. This is a question that you have to show your work. If you put your units up here with the givens, you're actually good to go now. So you know, if we're going to rearrange this to solve for r is v squared over p, and r will be 120 squared over 40. You'll get your answer. The math is the easy part. What also makes this chart great is that you can find essentially anything. So here, for example, let's look at the 60 part. You know both the power and you know that potential difference. So with the equation P equals VI, you could easily get the current. Well, you could do that in all of the columns. Further, you can now, or just like we did before, P equals V squared over R, get the resistance. So actually we'll stick with red. So the resistance here, and there's another way to get resistance, which is worth pointing out. You haven't seen it yet today, the VIR pyramid. So if we want to get resistance here, what we do is we cover up the R with our hand, and let's see, make ourselves a little, there we go. So if we cover up the R with our hand, what we're left with is V over I. And so you can easily solve for resistance in the parts. Once you have that all set, you can essentially fill in anything you want in this chart. You could come across and do the 1 over REQ equation. You could come across and you can sum the currents. And you could then figure out the power. Now, a convenient equation for power that's not in your reference table is actually that the power is sum. So 40 plus 60 plus 100, this actually will give you a total power 200 watts. Particularly convenient because for both series and parallel, it simply sums. Anyway, you can get anything you need. So this question may only ask for the resistance in that part, but you're ready. You can handle any question at this point. All right, let's go down here. Describe what change if the power, let's see, if the 60 watt were to burn out. Now, you got to watch out for this concept of burnout. Here's another one, burnout, and even 83, the circuit is disassembled and then connected in. Beware here, anytime a circuit changes, you want to redraw your chart. Yes, this may seem labor intensive, but realize this is going to happen at most probably once on an exam. So if they change the circuit, redraw the chart. Change the circuit, redraw the chart. And so you can very easily do this for question 83 and question 84 and get your answers. So question 83 asks about the 100 watt power if the 60 watt burns out. So what you'll end up doing is redrawing the chart with the whole, the 40, and the 100. And though some of you may realize that there are shortcuts to certain types of circuits when removing a resistor or a lamp, you're best off just redrawing the chart, follow the rules, so guarantee no mistakes. Finally, question 85, though we don't need to do this because, again, just set it up, realize when you have to set this up in series, the rules change. So as soon as you have to set up a series circuit, your whole part VIRP chart will now have the word series up in the corner, and you will instead focus on the series circuit rules, which of course are different. This one came up here for our parallel circuit rules. Okay, good. There's your whole part VIRP chart. Works every time. Okay, next. What do I do if I get a projectile with a curved trajectory? This used to be asked more. You never know. It could come back into favor. But essentially, if you have any sort of projectile that curves, and this again, sketch, 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 sketch. So you have a cliff, any kind of sketch. You have an angled projectile fired this way. Any kind of sketch where you see the trajectory itself is curved. You need an XY chart. And we actually included the R column, which is the resultant column, although generally speaking, that is seldom asked. So the XY chart separates your horizontal and your vertical givens. And this is a very useful thing to do, even if the question is multiple choice, even if the question is qualitative. For example, what's the acceleration? What's the horizontal acceleration? And it doesn't seem like there's much to do, but if you draw your chart, hopefully you're in the habit of writing acceleration in the x is 0. And so it makes that multiple choice question extremely easy. All right, one main focus point is, of course, you only use one column at a time with an equation. So you can either use the y column with PRT6 or the x column, but not at the same time. Let's go check out a live example. All right, here's a couple of nice questions. A football is thrown at an angle of 30 degrees above the horizontal. First move, sketch. Doesn't need to be beautiful, but try to make it roughly accurate. So there is your ground. And 30 degrees, less than 45. 45 is that mid-angle. 30 degrees, maybe something like this. So the trajectory itself, we peel off that velocity vector, it looks something like this. Okay, do we see a curve? Yes, we do. So, x, y. You can even put a little r over here just in case you need it, but not typically asked. Okay, so what are all the different things we need to know? Well, first off, regardless of the details of the problem, we know for certain the acceleration in the x is 0, and the acceleration in the y is 9.81. However, warning, if your problem goes up and down, you will run an issue if you don't keep track of the negatives. So my recommendation, call up positive, acceleration is always 9.81 down. There it is. Give that a negative 9.81. And some of our other problems, like the drop problem and the cliff problem, you don't have to worry about that. Everything is down. So what else did they tell us? Oh, they told us the angle here was 30 degrees. They told us, and watch out for this phrase, above the horizontal. That does not mean that the problem is horizontal. It just means start at horizontal, start here, and then move your way up 30 degrees. There's your angle. All right, the horizontal component of the initial velocity. So there's a lot of words there, but initial velocity is VI. Horizontal component is x column. So they're telling us the VI and the x is 13 meters per second. The vertical component, so that's in the y direction of the initial velocity, is 7.5 meters per second. Okay. Now, the first question, though it doesn't seem like it would be answered by a chart, in fact it is. So don't stop. Let's fill in the rest of what we know. Since acceleration in the x is 0, going back to your OPRT, there it is. If acceleration is 0, then the change in velocity must be 0, aka constant velocity. So the VF in the x is 13 meters per second. Okay. We know a few other things as well. What goes up must come down. So if the VI in the y is 7.5, the VF in the y, as it reaches the ground, will also be 7.5 in the negative direction. All right. Let me just cover up this little spot so that does not look like a negative. Good. All right. There's even another given we know. Since it goes back to starting height, the displacement, and it's worth writing, by the way, VF at the end, not at the peak, VF at the end. Displacement in the y direction at the end, it comes back to ground level, it's actually 0 meters, off overlooked given. All right, so the question here says, sketch the relationship, question 60, between horizontal displacement, that's dx, versus time. And if you remember back in our earlier video, we talked about relationship graphs. You must think about any graph versus time. Versus time, you're not just going to pull straight off the reference table. You have to think about what's happening. Well, displacement in the x versus time, as time increases, what happens to displacement in the x? Well, it starts here, and it's clearly moving in this direction. So you know it starts out at 0, and it's going to end somewhere up here. The question is, how do those two connect? Well, you may remember that because of this acceleration 0, constant velocity that our blinking light diagram actually showed, nice steady spacing as you went across the horizontal direction. That again is your constant velocity. Well, how do we connect constant velocity to a d versus t graph? Answer, slope. So this connects back to our graphs. The slope of a d over t is actually v. And so since v is constant, as you see up here, the slope must be constant. It's not 0, keep in mind. So a constant, non-zero slope, boom, looks like that. Good. Now, question 6162, calculate the total time the football was in the air. Well, we have a beautiful chart set up. T at the end is what we're looking for. You're only going to use the Y column because that is where our question mark given is lying. And pick an equation. The easiest equation is probably this one. You know VF at the end, you know VI, you know acceleration, get time. Notice where the negatives come into play here. If you did not keep track of this negative 7.5, you would then plug in 7.5 equals 7.5 plus 9.81 t. You'd end up with t equals 0. Well, that's not the point we're looking for. We're looking for the other end point. So you need your negative 7.5, and you'll get a better answer here. All right. So there's your XY chart. If you want the details of XY charts in different scenarios, such as horizontal projectiles, well, then you should go and look at the topics to know, the things to remember in topic 2, which is on the drive. Okay, on to the next page. Yes, this one's 2 pages, but not as bad. What do I get? What if I get a problem with masses, velocities, 2 objects, and they're somehow interacting, like they push off each other or they bang into each other? This scenario, which is often a cannon and a cannonball, or 2 carts with a spring between them, or even a gun and a bullet, these are often conservation of momentum. Not every time, but often. So, how do we set these up? Well, often you're going to set up a P before equals P after chart. So let's go check that out. All right, here's one. A 7.28 kilogram bowling ball traveling east. Again, a sketch is your friend. Here's a bowling ball. Let's say north is this way. So it's traveling east. Collides with the 5.45 kilogram bowling ball. Traveling west. Now, as we did a lot at the beginning of the year, all of these vector quantities, as soon as you see the word east or west, it's worth your while defining one as positive. So I'm reading along meters per second. East! Come over here, call that east positive. Of course, that means your west will be negative. That is going to save you on a problem like this. Okay, so determine the magnitude of the total momentum after the collision. That's actually not a bad question, but the structure will help us. So we know we have a before situation, we have an after situation. Before, we have the mass of, let's call this ball 1 and ball 2. So the mass of 1 is 7.28 kilograms. The mass of 2 is 5.45 kilograms. The velocity of 1 before is 8.5 meters per second. And it is going east, so we'll keep that positive. The velocity of 2 before is 10 meters per second, but it is going west, so this one gets a negative. Now, they want to know the total momentum after. So momentum total after, kilogram meters per second. So how do we actually go about this problem? Well, you need to look at P before equals P after. Now, not everyone sets up exactly how the givens do here, but they all use the same structure. And sometimes you can take shortcuts, but you don't need to, because this method always works. There's your P before equals P after. And of course, if you notice, momentum is just M times V. So really what this is saying is the MV of ball 1 plus the MV of ball 2. And that's going to equal the momentum after. Now what I'm realizing, and maybe you miss it, what I'm realizing is they actually want the total momentum after. So some of you may jump to this, M1V1 plus M2V2 after, and that's okay. But what you'll notice is that really all they're interested in is this entire thing, which is the total momentum after. But with the givens we have, let's see what we can do. So 7.28 times 8.5 plus 5.45 times negative 10, and you're going to get a number over here. Whatever this number comes out to, that is the total momentum before, which of course means it is the total momentum after, and there's your answer. So just beware, this general setup is just manipulated slightly different ways. One way it can be manipulated is they can actually give you the speed of ball 1 after the velocity and then ask you for the velocity of ball 2. It's not a hard thing, just plug in the numbers. Or they can make this an explosion problem, where before neither of them are moving, so everything on this side would be 0. Afterwards, you would have to plug in M's and B's. So all the different possibilities of colliding and sticking together, of colliding and bouncing apart, of starting together and exploding apart, all those different possibilities are both discussed here in our chart. And in the things to know, if you look at topic 3, you'll find that there's a description of all those different scenarios. However, it's not worth memorizing. Really, it's worth thinking about it. There are two objects. Generally, there are two objects. What are they doing before? What are they doing after? And if you put that all together, you will get this question. All right. Now we have another big conservation law. So the first big one was up above, conservation of momentum. Here we have conservation of energy. Two big universal laws that always hold within a system. So let's check out question 15. Now, it's all words. Why would we need a diagram? Because the diagram sorts it out. Let's go. A rough horizontal tabletop. Oh, look at that rough tabletop. So here's a block. It's sliding, which means it has some level of motion. I do not put my velocity arrows or vectors on the block itself. Reserve the block itself for force vectors. So we have a forward velocity, and then it comes to rest. So at some point over here, the velocity is now 0. There is an increase in, and now they have energy, 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 energy. Well, let's think about that. What we practiced during the year was take the two locations, location 1, location 2, sum up all the energies at each. So at location 1, let's see, does it have PE? No, because it has no height. Does it have KE? Yes, because it has speed. Does it have Q? Not yet, because literally at the moment it starts, that's where we start our 0Q. So not yet. And does it have PES, any spring energy? Well, there's no spring involved. So there is your total energy. Your total energy is all kinetic at the beginning. Then, go to position 2. Does it have PE? No, there's no height. Does it have KE? No, it stopped moving. Does it have Q? There was friction. Look at all that hot thermal energy. Does it have PES? No, there's no spring. So here, total energy is now, well, yes, there has to be Q. Q, with friction, they do heat up. So what actually happened here? You had a conversion of kinetic energy to internal energy. So there is a decrease in kinetic, and there is an increase in, here it is, internal or thermal energy. So if you look at this from conservation of energy, it all comes together. All right, let's check out this one. Very similar sort of problem. A compressed spring. Compressed springs, they love those in energy problems. And launch. Ooh, I'm thinking already. So compressed spring. It leaves the toy with a horizontal. So here's how the toy must look. There must be some spring toy. Here it is. It's got a little, what's on the end of it? Something on the end of it. Here it is. And it's going to fire this thing off in this direction. Okay, so here it is before. And the object, well, it's really like this system here. And then a little while later, the spring will be extended, and the toy will have left the spring. Now, really the way I drew this, and I'm glad I drew this because it's not a good drawing. You want to separate it into how it is before and after. Before, it's not actually in motion, so get rid of that. After it's in motion. And you need to be very careful with your two locations during energy conservation, or your two situations, 1, 2. You want to keep track of very carefully what's actually happening at that moment. So here we have a compressed spring. Here we have a moving ball. Okay, so if we look at the energies, we know for certain here, PEG, well, since it's at the same height, it's talking about a horizontal launch, then no, it's going to end up at the same height over here. So that's not changing anything. Does it have any KE? Not at the beginning, it's not moving. Does it have any Q? Never at the beginning. Does it have PES? Yes, it's a compressed spring. So the total energy is just the PES. Over here at the end, does it have speed? Absolutely. Does it have Q? This is the very beginning of a problem, though they didn't state it explicitly. This is really a neglect friction problem. And then does it have PES? Well, there's a spring, but it's no longer compressed, so the answer is no. The total energy is now KE. So really what happened is energy converted from PES to KE. And so if we check out our reference table, we can calculate these individually. Now, I've assumed, but it's worth restating, anytime you have PE, gravitational PE, there's a dependence on height there. KE depends on velocity, PES depends on that stretch or compress, and Q doesn't have its own equation, not in our course, but it does depend on that friction, that rubbing over a displacement. So really work done against friction. Okay, so here the question says, how much PES was in the spring? Well, if you notice the givens, you're provided with a mass, you're provided with a speed. These very nicely fit into the KE equation. So you can figure out the KE, and then clearly since PES became KE, it'll be the same number. Watch out, because the Regents will do this. This says grams, and I know from your year in chem you're not too bothered by grams, but our equations, when you plug in, require mass to be in kilograms. Just as a quick reminder of what to do, if you say 5 grams equals some number of kilograms, just put a big X in there and solve for X, and that will tell you how many. If you're ever uncertain, I have 5 grams, how many kilograms is that? Well, if you look it up in your reference table, 5 grams equals some number of kilo on your reference table means 10 to the third grams. Divide both sides by 10 to the third. The grams cancel out here. You will get 5 times 10 to the minus third, 0.005. That's the right mass. Plug it in, you'll be good to go. Very last one of these we'll look at very quickly. Notice again, by the way, that's why I went over this little conversion. They provided you with grams. So you have to be ready to turn that gram to kilogram. So if you notice here, we have a tabletop and a cup. So the cup falls and it hits the ground. The things to watch out for, they tell you how much. Look at the energies. At the top, it's got PE. No Q yet. No KE yet. No spring. Is your total is just going to be equal to that PEG. At the bottom, it's got no height. It does have speed as it reaches the ground. In fact, they told you how much. There's no PES because there's no spring. And whether there's Q, well, they actually asked the question, what is the total amount of energy converted to internal? So from that, you can assume there is Q, and you'll have a total. This same total fits here. Whatever the total was at the beginning, it will be at the end. You know the KE, you know the total, solve for Q. So there's your energy conservation. All right, one to go. The one to go is, how do I deal with force questions? Again, this is big time. This is diagrams. Let's go check out force questions. Here's a nice force question. You have a block on a table. So, what do we got going on here? Generally speaking, label up your block. Label up your diagram. We have an FG. We have an FN. We have this one as our external force. There's some pull. That's our 4 newtons. And when they're talking about the materials, copper block, steel table, oddly particular. Yeah, well, that's because they're telling you there's some kind of friction involved here, too, coming back this way. And then finally, don't forget your buddy, F net. And we may not know these yet, but we know they exist. All right. So based on what we've read, first question is find the weight of the block. Well, on your reference table, weight is Fg. So, OPRT. There you go. Here's a nice Fg equation down here. Cross multiply mass times that gravitational field strength. So that's easy enough to do down here to get the weight. Of course, there are no diagonal pulls and no ramps, so your normal force will match the weight in this case. What about this next one? Calculate the force of friction. Set your givens. Friction is what you're looking for. Now, it would be nice to just have friction match this 4 Newton external. But in order for that to be the case, you need F net to be 0. And no one said that. No one said constant velocity. So the other thing we can do is just be reference table hungry. Where's our friction equation? There it is. Coefficient times Fn. Ff is Fn. Now, you know the weight and the normal match. It's part of why the diagram is there. So your answer to question 66 gives you the normal. The coefficient, that comes off the reference table too. In fact, when those givens are oddly particular, you should go look for a table that has them. And so here is the table that has them. This question is about copper on steel. It is in motion, so we use the kinetic coefficient, 0.36. Plug it in, you'll get your answer. Now, the next one is really the one where this diagram comes in handy. Determine the net force on the block. Well, once you know the external and once you know the friction, well, that's very easy. Normal and weight balance. External minus friction will be some number. That number is right here. That's your net force. There is, in fact, a net force in this problem. And so this is actually a nice review. If there is a net force, well then, based on this equation, there must be an acceleration. And if there is an acceleration, based on this equation, there must be a change in velocity. So it's very simple here. If there's a net force, you know there's a change in velocity, and just depends on which way it's going. So this block is being pulled to the right. If the net force is to the right, well, then you're pulling in the direction of motion. Of course, it's going to speed up. If you pull opposite motion, then it's going to slow down. So your answer would be speed up. Now, question 5 is a nice one. It's actually very easy. People often take shortcuts. Student throws a 5 Newton ball straight up. What is the net? I see net force. I am drawing a diagram. Ground. Ball. Draw all the forces on the ball. Max height? Well, we know gravity is acting on it. What else? Normal? No. Normal forces from the ground. It's not touching the ground. There's no normal. What else is there? Maybe you'd argue friction. Well, what happens at the max height? Max height, it stops momentarily, which means it's not in motion, which means even if there is air, at this moment, there's not actually any air resistance or friction. So there is the entirety of your forces, which means the net force is the weight. It points down, obviously. And so whatever the weight was, 5 newtons, there's the net force. The way the weight pointed is the way the net force pointed, down, done. Last one of these is the glorious elevator problem. Elevator problems are not actually bad. Elevator, rider. There are only 2 forces within every elevator problem. Those forces are old reliable, weight, and then the force from, here they phrased it, the upward force of the elevator floor on the person, aka the normal force. Now, I always draw the normal force as a stub because we don't yet know how big is that normal force. The normal force changes. The weight remains the same. So the normal force actually connects to the net force. In this case, the elevator is accelerating down. Well, from our relationship we saw before, net force, acceleration, change in velocity, if the acceleration is down, then the net force must be down. So we come over here. If the net force is down, now look at your forces here. The net force is the summary. The net force is basically put it all together and who wins. If it's down, then the downward force must be bigger. Keep my normal force short. There is my free body diagram. Clearly now, how does that normal force compare to the weight? Less. And there are your force diagrams. Of course, there are many other versions of force diagrams, such as pulled at an angle or on a ramp. But those are more into the detail than the process. Here is the process of just add all the forces, look at the net force, see how they interact. All right. So, yay. You're done with part 5. That's the last of the big parts. Congratulations. Hope to see you during the next part of our video series. Regents. Physics. Warm up.